Okay, so we talked about sequences yesterday. I want to recap a little bit, and then Tipe has a couple of questions, and then we'll talk about our we'll talk about our lesson for today, which is recursively defined sequences. Justin, if you'll hit the door, please. That's your door. In terms of definitions, a sequence A sub n is a function whose domain is natural numbers. That's right. Which we abbreviate as Z plus, natural numbers. By the way, when you see it in the literature, they do a fancy script kind of Z, like this. So Z plus. I suppose I should learn to do that somehow. And then we talked about convergence. We said that A sub n goes to L if the limit as n goes to infinity of A sub n is equal to L. Another way of putting that is for the epsilon greater than 0, there exists an n such that the distance between A n and L is less than epsilon for all n greater than n. So that was the general theory. Then we looked at two specific and important types of sequences, arithmetic and geometric. And do you guys know the forms? Arithmetic. A(n) is equal to?
A plus 1 plus, A sub 1, sorry.
Okay.
Plus n minus 1 quantity times d.
Times d, good. And we think of this as point slope form, essentially, in which d, the common difference, serves the same role as the slope in a linear function, and a sub 1 is the point that corresponds to n equals 1. Meanwhile, our geometric sequence, which is even more important than the arithmetic sequences for us, a sub n is equal to? That's it. And so this plays a role similar to the exponential functions. Okay, that's our material. Now for your questions.
So with number 39, which is a sub n equals n sine of 1 over n. Are you supposed to like turn it where it's more accurate, please? And I just want to take this as a limit problem. Because it looks like the form is
Okay. Give me the general idea for dealing with the form infinity times 0. Or 0 over 0, exactly. So we need to do some algebra here with this. Can you think of any possible algebraic things that we might do? Yeah, or just over 1 over n. Yeah. Probably the easiest way to see it. And now as infinity, as n goes to infinity, 1 over n goes to 0. So my form has now been converted into the form 0 over 0. And at this point, we can see it either in terms of substitution, which is how I like to see it, or we can see it in terms of L'Hopital, because this is L'Hopital's algebra. Both are equally easy. If I view this in terms of substitution, then I would do something like let w equal 1 over n, because that's my inside function. And I can substitute my troubles away. If I let w equal 1 over n, then I am taking the limit as w goes to 0 of sine w over w. I know that limit. So this is actually a famously disguised form of the famous limit as beta goes to 0, sine beta. If I were to do L'Hopital's, I would get much similar, same kind of thing. I'd get cosine 1 over n times negative 1 over n squared over negative 1 over n squared, cancel, let n go to infinity, cosine of 0.
And the, number 43,
Mm-hmm.
the induction, I think that's
Uh-huh. So we're actually going to use induction later on today. Let's go ahead and do a quick review of how that goes. What was the thing that you were supposed to show?
A, so then equals 1 over, and exclamation mark.
And I said show that. A(n) goes to 0. Did I say show that A(n) goes to 0? No, what did I say?
You just said, do number 43 is an induction.
Well, what is the question asked for us to do?
Use sandwich theorem.
Use sandwich theorem. Got it. I actually don't think this is a great candidate for induction, so no wonder you hit a wall here. Let's do it the way that they suggested. Can you think, first of all, do you remember what factorial means?
1 plus 2.
No, the key is its multiplication. So we're actually looking at n times n minus 1 times n minus 2 all the way down to 1. Okay? Now, if we're going to use the sandwich theorem, what we have to do is we have to find some sequence that is a lower bound for 1 over n factorial that goes to 0 when it goes to infinity, or does something when it goes to infinity. We strongly suspect this is going to go to 0, right? Right, very low bounds. And we also have to find an upper bound, some sequence that is bigger than 1 over n factorial that also goes to infinity. Now the lower bound and the upper bound are a little bit tricky because I'm dealing with a reciprocal right here. But I think we can probably do it. Can you think of some really easy function that is always less than 1 over n factorial?
Just do 0.
Good. Very good. 0 is a function that is definitely always less than 1 over n factorial. And it goes to 0. Yes. How about over here? One. Well, 1 works, but it doesn't go to 0.
Oh, okay, yeah.
1 over n?
1 over n. I like that. 1 over n is definitely always greater than or equal to 1 over n factorial. Equal when n is 1. Greater when n is larger. And actually also equal when n is 2. Greater when n is larger than that. And it also goes to 0. So, since the limit as n goes to infinity of the two bounding functions are both 0, we conclude that the limit as n goes to infinity of 1 over n factorial is 0. So sandwich was a good choice here. Elliot, you look like you have a question.
No.
Right.
Because, like, in the middle, like, what do you think? Like, the limit n goes to 0, under the infinity, 0 equals to,
Equals 0. I'm just saying that the two of these have the same value. I'm not replacing this with that.
Okay.
Yeah. This is the standard move with sandwich theorem. You take your two bounding functions and you say that they have the same limit. Okay, well, let's jump into our lesson for today, which is recursively defined sequences. Are you good? Okay. Recall that yesterday we had two different forms that we could find a sequence in. We could have a closed form where I give you a specific function that a sub n is equal to. This is a closed form, and we like closed forms. They're easy to work with, and we can tell convergence pretty easily most of the time, so on and so forth. We have enumerated form, in which you get the first few elements, maybe in this case 3/2, 1, 3/4, 3/5, and it is your job to figure out the pattern. And now we want to consider a third form, which is the recursively defined form. Or the recursive form. And in the recursive form, you get two pieces of information. First of all, you get initial values usually the value a sub 1. And then you get a recursion relation that tells you the value of a sub n in terms of previous values. For example, a sub n equals a sub n minus 1 plus 3. The recursion relation gives us a sub n in terms of previous values. In other words, it gives us a pattern. And in this case, the pattern is saying the next term is equal to the previous term plus 3. Now, our recursive form is very, very convenient if we can discern an easy pattern for it. That's really the purpose. And it's also very flexible because it allows us to define really, really interesting kinds of series. So this would be one example of a recursive form. Here's another example of a recursively defined series. Notice that I have an initial value, and then I have a recursion relation that defines that series. And here is yet another example of a very famous series called the Fibonacci series as sequence. Fibonacci sequence, where f1 is equal to 1, and f2 is equal to 1, and f of n is equal to fn minus 1 plus fn minus 2. And in this case, what I'm doing is giving a recursion relation in terms of the two previous terms. The downside of the recursive form is that it can be hard to understand the logic of it in some ways. What is this thing? What is that thing? What does the Fibonacci sequence do? What are its properties? So one of the common moves that we have is to take a recursive form and immediately enumerate it to try to see what we're looking at. So a basic move is to go from recursive form to enumerated form. If I take that first one that I gave you, A1 is equal to 2, and AN equals AN minus 1 plus 3. Now I can start enumerating by generating successive values of AN. So if I start with 2 as my first value, then to get to the next value, according to the recursion relation, I add 3, and that gives me 5. And then to get to the next value, I add 3, giving me 8. And then to get to the next value, 11, 14, etc. Oh, that's what this is. What famous type of sequence is this? It's an arithmetic sequence. Of course it is. So that because it is arithmetic, I can immediately say that its form, that its closed form is 2 plus n minus 1 times 3. That's a little bit off, but I'm going to write it as 3 times n minus 1. Does this make sense to everybody? How we go from the recursive form to the enumerated form, and if you recognize a special sequence, then you can also write a closed form. Let's do the same thing for this sequence right here. Why don't you guys go ahead and enumerate the first 4 terms, and then see if you can come up with a formula for it. Okay, and so if, let me go to the next page here. If G1 is equal to, did I remember this correctly? 2, 3, yeah. If G1 is equal to 2, and Gn is equal to 3Gn minus 1, then what are the first 4 terms of my enumerated sequence?
I got 6.
Hopefully you got 2 first.
Oh. Shoot. Alright, ignore you then.
Carry on. 2, 6.
2, 6, 18.
And what kind of sequence did you identify this as? It's geometric. It kind of helps that I labeled it as G. Yep. And what closed form do we have for it?
Is 2 and 3. 2 PV, and minus 1.
To be minus 1. Exactly so. Okay. All right. Let's now come back to our Fibonacci sequence and consider an interesting thing about our Fibonacci sequence. Fibonacci sequence has a huge history, and the history starts in the 13th century, actually. Fibonacci writes this treatise on the reproduction of rabbits. And he says, let's suppose that you start with a pair of rabbits. Now, the thing about rabbits is they take a year to mature. So after 1 year, nothing has happened. You still have a pair of rabbits. So F1 is one pair of rabbits. F2 is one pair of rabbits. So we're good. Then they begin to reproduce. And when they reproduce, what happens is that the mature pair of rabbits, are the ones that are at least 2 years old, and let's just suppose that they each give birth to a pair of rabbits. Now that's not realistic because they usually give birth to like 6, but there it is. So let's suppose that that the mature pairs each reproduce themselves in the same number. So that we add the number of mature pairs to the current number of rabbits that we have. Therefore, in the second year, we will end up with the amount of rabbits that we have plus the number of new reproduced rabbits. So we can now start to enumerate what we get. For the first 2 years, 1, then they mature, then they reproduce, so that we now have 2 pairs. Then this pair reproduces again, adding to our total. Now we have 2 mature pairs, so that they reproduce. Now 3 mature pairs, so that they reproduce, etc. So that we end up with this really neat, interesting sequence. Well, in some sense, this would have been just an intellectual curiosity. But it turns out that the Fibonacci sequence has its fingers in all of these different branches of math. For example, the most efficient algorithm that we know for finding the greatest common factor between 2 numbers is Euclid's algorithm, in which you subtract a multiple of one number from the other and continue that process until you get down to a common factor. Basically, until you get down to 0, and that last step is your common factor. It turns out that the Fibonacci sequence is the least efficient sequence of numbers. If I give you a Fibonacci pair, basically, then it's going to take the greatest number of steps in order to achieve. So the Fibonacci sequence puts an upper bound on the efficiency of Euclid's algorithm. The Fibonacci sequence shows up in biology all over the place. So if you take a look at the pattern of numbers of pine cone whorls around the cones, they form the Fibonacci sequence. Yes, and other biological applications are similar. And one more thing, and that is that there's a very interesting relationship when we take a look at the limit as n goes to infinity of the ratio of fn plus 1 to fn. If I take the ratio of successive terms here, let's do that mentally. 1 over 1 is 1, 2 over 1 is 2, 3 over 2 is 1.5, 5 over 3 is going to be 1.6, yeah. 8 over 5 is going to be 1.6, that's right. And 13 over 8, that's going to be tough, but it's pretty close to 1.6 as well. As I continue on out, you can see that I'm getting numbers that are very, very close to 1.6. So we wonder, is it possible that as n goes to infinity, that this ratio settles out to a well-defined number? And it turns out the answer is yes. And we can find that number. How? We can find that number by appealing to the recursion relation in this way. Suppose this number is equal to some number, let's call it phi. Phi, by the way, is called the golden mean sometimes. Then, the limit as n goes to infinity of fn plus 1 over fn, appealing to my recursion relation, fn plus 1 is equal to the sum of the previous two terms, fn plus fn minus 1. But now just do a little bit of algebra and write this as 1 plus fn minus 1 over fn, like so. And now we come to a remarkable thing. Notice that this ratio, the ratio of the next term to the previous term, is mirrored right here. This is the ratio of the previous term to the next term. And as n goes to infinity, fn over fn minus 1 has to be the same as fn plus 1 over fn. So that this is 1 plus 1 over phi. And what we have discovered is that therefore this phi satisfies the relationship that phi equals 1 plus 1 over phi. That's an equation in one variable. I can solve for it. Multiply both sides by phi. Hey, we got a quadratic. And we get two solutions for phi. One of them is negative, and so is therefore excluded. And we get therefore that the golden mean is equal to 1 plus root 5 over 2. The golden mean has applications in art and geometry all over the place. I don't know if you've ever heard of the golden mean before, but it basically represents, and you can show this geometrically, it represents the proportions of a rectangle such that when you cut off a square, you end up with a new rectangle that is scaled proportional to the old rectangle. And it is considered a particularly appealing to the eye kind of thing. So the Parthenon-like shape.
Oh,
Yep. And so this comes from Fibonacci sequence as the limiting case of the ratio of the next term to the previous term. I really should say the next term to the current term, to be precise. Okay. Let us now consider the relationship between recursive forms and proof by induction. I want to remind you of how proof by induction goes. The idea is that we want to prove a statement about n, prove P of n. And the way in which we do it is to first establish a base case. Excuse me, these proofs usually have a lower bound right here. In fact, they must have a lower bound in order to be successful. And so first we show that P of n0 is true, and we call this the base case. And then we show that if P of n is true, then that implies that P of n plus 1 must be true also. And this is called the induction step. And If we have done that, then what we have done is to establish an induction chain so that the base case implies the next case, which implies the next case, which implies the next case, and so on. So these two things together get me to here. Well, it turns out that recursive sequences are really, really tailor-made for proof by induction. Let me show you what I mean. Let's consider a recursively defined sequence like this. A1 is equal to a value A, and AN is equal to AN minus 1 plus D. Let's show that if this is the case, then AN is always an arithmetic sequence, and vice versa. Now, the proof in the reverse direction is easy, so let's do that first. Let's do the proof in the reverse direction first. And mathematically, this is the way that we denote that a lot of times. So we are going to start with this and get to here. But that's pretty easy, because if AN is equal to A times plus N minus 1 times D, then clearly A sub 1 is equal to A. It's just a matter of plugging in. And if I compute A n minus 1, then it's pretty clear to see that AN is equal to A plus N minus 2 times D plus D. In other words, I'm peeling off a term of D. And so therefore the recursion relation applies. Probably an easier way to do this would be to rewrite the recursion relation in terms of a difference. That the difference between the two terms is equal to D, and then you can just plug in and subtract and get that difference. You look suspicious.
I don't understand how, like, when you're doing the A sub n, like it equals A plus, no, A plus n to the negative 2. I mean, A n minus 2D plus D.
Oh, all I did was to plug in N minus 1 into this formula.
But for like the one below that,
Oh.
how do you got to?
Oh, I see. How I got from here to here. Yeah, that's what I was saying. It's probably easier to see it like this. What I did was just kind of a cute trick. I've got N minus 1 D's that I'm adding on. D equals D plus D plus D plus D, N minus 1 times. And I just grouped them so that I had N minus 2 of them here, plus another D.
So we do N minus 2 plus 1.
Just
And then still-
yeah, just combine these two.
Okay.
Yeah, and common factor these. Okay, so the reverse direction is easy. We don't need any induction for that. But for the forward direction, we're going to need some induction. What we want to show is if these are true, then we have a closed form that is the desired form. So we consider, first of all, our base case. And our base case is going to be n equals 1. So that what I have to show is that the closed form gives the right answer. And the closed form is A plus 1 minus 1 times B, which is equal to A, which is equal to A sub 1. And what that means is that A1 has the right form. Now for our induction step, we're going to assume that AN is equal to A plus N minus 1B. And we are going to show, therefore, that AN plus 1 has the right form. So we start with the recursion relation, which is the given thing right here, and we see that AN plus 1 has to equal AN plus D. And we can now substitute our induction hypothesis, which assumes that AN has the right form. And when we substitute our induction hypothesis, then lo and behold, we get A plus N minus 1B plus D is N times D. And to show that it absolutely has the right form that we're looking for, we cleverly rewrite N as N plus 1 minus 1. Now what have I showed? I have showed that if AN has this closed form, then AN plus 1 necessarily has that closed form. In other words, I have showed that for all n greater than or equal to 1, that A sub n is equal to A plus N minus 1 times D. Now the key steps to generating your induction step right here, because I think we all agree the base case part is easy, right? The key things to generating the induction step are to, first of all, identify what your induction hypothesis is going to be. That part is easy. The induction hypothesis is going to be what you're trying to prove. And in this case, I was trying to prove that if this stuff is true, that has to be true. This is going to be my induction hypothesis. That's what I'm going to assume. And the induction hypothesis I can write as P, as the proposition P sub n, that AN is equal to A plus N minus 1B. So then the next thing, in the next step in creating a good argument for induction is identifying what P sub n, P of n plus 1 ought to be. And P of n plus 1 is going to be found by substituting n plus 1 into the induction hypothesis. So that when I substitute n plus 1 on the left side, I get A sub n plus 1. And when I substitute n plus 1 on the right-hand side, I get A plus n plus 1 minus 1 times B. So that what I'm trying to prove is that this equals this. That gives me the goal that I'm working for. Then I fill in the details by just setting it up with whatever givens I have. In this case, I was given the recursion relation. And at some point, I appeal to the induction hypothesis to substitute. So that thought process worked like this. First, I identify the induction hypothesis, and I assume that. Then, I start on the left side of my P n plus 1 and apply my given, which is that recursion relation right there. And then I take that given, and here I use the induction hypothesis to substitute. Clean it up, and show that I get to the right-hand side. That's the basic thought process that we undergo all the time. Along the way, what I've accomplished now is to show that the arithmetic sequence is defined recursively as the next term equals the current term plus d. In other words, each term is d more than the previous one. And that's the pattern that we saw yesterday. Let's do the same thing for the g matrix. If the first term is a, and the succeeding terms are r times the current term, then Gn has the closed form a r to the n minus 1. That's what I wanted to show. All right, help me out. Base case. First of all, what n do I use for my base case? N equals 1. And now substitute n equals 1 here and there and show that it works. Uh-huh. Okay, so what we did here, just to make sure the logic is clear, first of all, we took from the if part of our statement right here, we took G1, which we knew to be A. And then we showed that if I substitute 1 into this expression right here, I get the exact same value. And so that shows that when n equals 1, this statement is true. G sub 1 equals A implies that G sub 1 equals A. So that's the base case. Now let's do our induction step. First of all, give me the assumption. What am I going to assume? And really, this should be an implication. So really what I'm assuming is, if this stuff is true, then this is true. So the full, let me put it like this. But the important part of this is the conclusion that we have right here. Okay. So that is Pn. Now, what is the conclusion for Pn plus 1? P of n plus 1. And we're going to find that by substituting n plus 1 into our conclusion over here. It's just a mechanical step. Uh-huh. No, there's no subscript. Or a comes right in. Yeah, that's exactly it. So this is the conclusion that I'm going to try to draw here. And I'm going to now prove that this conclusion is true, given this assumption, by starting at the left-hand side and getting it to be equal to the right-hand side. So we're going to start with the left-hand side. G sub n plus 1 equals. And now I'm going to rewrite G sub n plus 1 using the things that I have given. The first thing that I have given is this guy right here. And the second thing that I have given is my recursion relation right here. Oh, that was supposed to be G. Here's my recursion relation. So let's take that recursion relation and apply it to G sub n plus 1. According to my recursion relation, G sub n plus 1 should be equal to R times G sub n. Exactly so. So I can take Gn plus 1 and rewrite it a little bit. Now, let's do a little bit of substitution. What do I know about Gn? G sub n. A-R-N-minus 1. There you go. So, 1 over 2 times 1 plus 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 exactly what we were trying to prove. So that if this statement is true, it necessarily follows that this statement is true, and P of n implies P of n plus 1, and we're done. Does that make sense?
So should we like write the map part also?
Over here?
Yes.
Yeah. This is scratch work for you, but it's really helpful. It's extremely helpful.
Thank you.